A skateboarder stands at the edge of a dry swimming pool. The pool's floor varies smoothly from the shallow to the end, as shown in the figure above. The skateboarder's mass is 55 kilograms. That's reasonable. Without the skateboard, the mass of the skateboard is 1.6 kilograms. The pool's deepest point is located at 3.4 meters below the pool's edge. First, the skateboarder checks her skateboard by rolling it down by itself from the shallow end's edge of the pool. To find the skateboard edge of the pool, to find the skateboard's rising. So, myself for the challenge of the pool to find the skateboards. Okay, 0.2 meters below the edge of the pool before sliding back. Okay, so right here, 3.4 meters, and then the skateboard comes up to 3.2 meters. That's a 0.2, not drawn to scale. So basically, it comes up 0.2 meters. Before sliding back, what was the work done by friction on the skateboard during its first passage across the pool? Okay, so the way I'm going to look at this is balance of energy. So basically it's saying we have a skateboard up here, rolls down this way. Oh, that's terrible. There we go. So the skateboard rolls down this way and then comes up just a little bit and then rolls back again. And so what I'm going to do is I'm going to do a balance of energy from this point here where it starts to this point over here. And so what I'm going to say is energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final. And then I'm going to add in, I'm going to call it work due to friction. So normally you wouldn't have this extra work term in here because you have a conservation of energy. But we don't really have energy is always conserved, but it's not all accounted for necessarily in these terms because we have a friction as well, which is kind of like an energy loss. And so that's if we didn't have this friction term, then it'd go up to the same height that started with. This energy loss due to friction, or transferred into sound and heat and such along the path, that's what's preventing the board from going all the way up to the top. So we're going to assume it starts at rest. So the energy kinetic initial is 0. We're going to say that before sliding back, that's going to imply that the energy kinetic final is 0. And then we'll have difference in energy potential. This will be initial minus final. So this one minus that one. Well, we know that that's going to be mass times gravity times delta height. So energy potential will be mgh. So when you find the difference at mgh, the mass and the gravity, they stay the same, but the height is different. And we know this delta h is the 0.2 that was discussed right here. And so we move that over there, and this will equal work due to friction. This one is, I'm going to put a little r there, that we know it's friction, not final. Okay, and this one I'm not really going to worry too much about the sign. What was done by the friction, so we can do this here. We can do, equals, so the mass of the board is 1.2. I think it's 1.2. No, 1.6. 1.6 kilograms. We have 9.81 meters per second squared is gravity, and then the height will be 0.2. And at this point, I'm not really worrying about the sign. So go to the calculator. There we go. Clear the RAM. 1.6. I guess the RAM was already cleared. I just cleared the message saying that the RAM was cleared. Times 0.2. I guess I could divide by 5. We have 3.1392. 3.1392. Is that even a possible answer? Yep, 3.14. Okay. So this is work friction. So if we look at our answers, we have basically 0, which we know is going to be wrong. And we have a positive number and a negative number. So now we're going to worry about, okay, what happened? Is this a positive or negative work? So what was the work done by friction on the skateboard? Okay, so I'm going to draw a picture of the skateboard at, let's say, this point right there. Change colors. You don't actually have to change color. Just use purple, dark blue. So we have, I'm going to represent the skateboard as a block. it's not a block, it's specifically rolling. And so we have motion, I'm going to write this as R, going this way, and we have friction going this way, force due to friction. And the equation for work is work equals integral F dot dr, where both of these are vectors. So a dot product measures how parallel things are. Another way of thinking of it is the cosine of theta. So the magnitude of this and direction will be F times R times, if F is constant, which we're assuming it is. I guess we can't in this one, but the direction we'll see, the theta will always be constant because friction will always be opposing motion. So theta in this case, we know though, is going to be, we could say it pi or 180 degrees, or if you just look at your circle, that direction. So the cosine of that is going to be -1. So what we're going to have is work will equal something, integral F times dr, small things put together, integrated sort of way, but we're going to have a negative out here. There's going to be a negative sign because the force and the motion are in opposite directions. And that's what I'm getting at here. So we used this, the balance of energy, to find out how much energy we lost due to friction. And then I'm using the idea of work equals integral F dot dr with little vectors, with the dot product, to find the sign. And since we know that the friction was the opposite direction of the motion, it's going to be negative work. So this is the motion of the skateboard. That's the force of friction. The work done by friction on the skateboard, opposite directions, negative sign. And so, long story short, the answer is going to be negative 3.14 joules. Now, if we go back a little bit and look at this, we don't actually really have to do any calculations to find this because we only have 3 possible answers. So we have 0, which we know is not going to be right because there's friction. Otherwise, it would have rolled all the way back up to the top. And then just using our analysis of friction and direction of motion being opposite, we know we're going to have a negative answer. Therefore, the answer has to be A. So that's one way we can approach that problem. I'd still recommend working it out. Of course, on a timed evolution, you're not going to have the luxury of going through all the details that I do, which is okay. Okay, 21. After adjusting the skateboard to nearly frictionless, okay, so now we're to a frictionless scenario. Skateboarder drops in on her skateboard from the shallow end of the pool. As she goes along the floor of the pool, she pumps, basically kicks the skateboard, and then exits the pool at the deep end's edge, same height from which it started, vertically upward with a speed of 4 meters per second. How much work did the skateboarder do on the skateboard during the run? Okay, so we're going to do the same process we did earlier. So kinetic energy initial, energy potential initial equals energy kinetic final plus energy potential final plus, I'm going to call this work due to, I'm going to say kick instead of pump, because if I say pump there, you're like, well, is this a hydraulic system or is there water involved? And it just unnecessary potential for confusion, a human performance trap, if you will. Okay, so this says same height from which she started. So that same height there means that the potential energy is going to be 0. Or the change in potential energy will be 0. So this might be a number, that might be a number, but when those numbers combine, or when you subtract it from both sides, they cancel out. So they're not actually necessarily 0 themselves. Well, we could if we said that the initial height was 0. So I'm good with that. So she starts at rest, so this will be 0. And so we have an energy kinetic final here and a work due to kicking there. So energy kinetic is just 1/2 mv squared. And I'm going to say it's equal to, I know I'm being kind of fast and loose with my negatives here. I don't worry about the sign yet. I'll figure out the sign later when I analyze the direction of force and the direction of motion, similar to above. So work kick, so work kick. So we're trying to find out how much work did the skateboarder do on the skateboard. Okay, so this will be 1/2 times mass, and the mass is 1.6 plus 55 because they're together. So I'm going to call that 56.6, which is really just 55 plus 1.6, times velocity, which is 4 meters per second, 4 meters per second squared, and that's already in meters per second, so we don't have to convert them to SI units. So this will be, I'm just going to go straight to my calculator, so we have 0.5 times 56.6 times 4 squared, I guess I could have done 16, equals 452.8 joules. And then if you look at the skateboarder at any given point, the force to propel it forward more will be this direction, so it'll be force due to kicking. And then the motion will be also this way. So when you do work equals integral F dot dr, the cosine of theta between these two vectors will be 0, which will equal 1 as opposed to -1, so it's going to be positive. So this will be a positive value for the work, which makes sense because friction slowed down the skateboarder, while this kicking, that speeds it up. So it makes sense the signs would be opposite from each other. So 452.8, I'm going to call that the 453 answer. How much air does she get? Here it refers to the maximum height the skateboarder rises. I'm going to say rises above the pool's edge. Assume the skateboarder remains in contact with the skateboarder. Okay? So in contact is important because that means that we can just treat it as one system. So here again, we'll look at it, this system. So we do energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final plus work due to kicking. Whoop. Get our canceling color. Ooh, gray. So this time here, maximum height. At the maximum height, it's going to come to a stop and then fall back down. And it's important that it's vertical because we also know that the horizontal speed then will also be 0. Therefore, the total speed will be 0. So she comes down like this, up like this, and then straight back down. So at this point here, 0 velocity, which is important. I guess 0 speed as well. So we know she starts at rest, ends at rest, which is important. We're going to say no initial potential energy. And so we're left with energy potential final and work kick. I guess I could probably put this work kick on the left side over here, but that's okay. My notation here is terrible, and that's okay as long as you kind of have an understanding of what's going on. So we're going to have mass times gravity times height. I would have to be a little bit more careful with this if I had more variables, but since it's just 2, I'm good with this. Mass times gravity height, that's potential energy, equals 453. And so we're looking for this height here. H equals 453 divided by 56.6. 56.6, which is the total mass. And then we'll have to divide by 9.81. Okay, we can do this. So we'll already have the answer up there. Divided by quantity, 56.6 times 9.81. And 9.8 would probably work. Click, and we get 0.8155. 0.8155. And that'll be measured in meters. Okay? Looking back at this, 0.815. So this would be the answer right there. Okay. So to backtrack, kind of look at what we did on this problem. This is basically just a balance of energy problem where we had our initial kinetic energy and potential energy. We had our final kinetic energy and potential energy. And then we kind of had something that went on between the two. First was friction, which opposed motion. And since you had the friction opposing the motion, you had negative energy, negative work done. And then we had the skateboarder kick, which was a positive work added. So when we had the work done by the skateboarder on the skateboard, that was positive, because when we looked at work equals integral f dot dr, we had our dot product, which is basically the cosine between the two angles. And we then looked at another balance of energy for the third part, which we then just related the potential energy this time instead of kinetic, and that was mass times gravity times height. So not too bad a problem, but did a good job of covering the basics of energy balance. So hope that helped. See you next time.